Hello friends, today we will study what is Dijkstra algorithm, the basic its implementation and why it is a greedy approach to solve any problem. To start with, let's see what is a Dijkstra algorithm and how do we define it. Dijkstra algorithm usually works for graphs which are single source multiple destination for the shortest path algorithm. Now what do we mean by single source multiple destination? It is when I need to traverse a graph from a source to a destination. It is not necessary that from a single source there will be only a single path existing. From a single source to reach to the destination, there will be multiple paths which will be existing. So, from these multiple paths or the multiple destinations which are existing in between the final destination, we have to find out the shortest path among them. That is where my Dijkstra algorithm comes into picture. It is usually used for solving any graph problem where we need to find the minimum distance travelled from source to the destination. Now, what are the requirements of the Dijkstra algorithm? Let's see that. Now, the first and the basic requirements of a Dijkstra algorithm is it works on a directed as well as undirected graph, but gives an optimal solution for a directed graph. Now, what do we mean by the directed graph? That is, from a source to the destination, between the two nodes, I have a line which shows an arrow that I am traversing from node A to node B. That is known as a directed graph. It even works for a undirected graph too. And the second thing is, it works on a weighted and unweighted graphs. But if I am trying to find a shortest distance travelled or the shortest path algorithm, then obviously I need some weights or some values attached between the two nodes or the vertices of my graph. So it works optimally for the weighted graphs and gives the best solution for the directed weighted graph. It can work for both as it does not have a basic requirement of only the directed and weighted graph. It can work even for undirected and unweighted graph. A greedy algorithm that produces an optimal solution, and the optimal solution is produced when we have a directed and a weighted graph. This is the basic requirement of the Dijkstra algorithm. It is a greedy approach as we keep on choosing whatever is a minimum possible distance for the multiple destinations which are existing from the source to the destination. It is greedy because we choose the minimum possible path, not the maximum one. So we try to satisfy or justify our need to reach the destination. Now, let's take an example. Now, in this example, I have a graph which is a directed weighted graph. As we can see, there are 8 nodes or vertices. All the alphabets which are written are known as nodes, and all the lines which are drawn between the two nodes are known as edges, and to each edge we have assigned a weight, so that we know which is the minimum shortest possible path to reach from one node to another node, that is from my source to my destination. And for this, to make it easy to understand and simplified to work on, we draw an initialized array in the form of a table. If you will see, initially all the nodes are listed, that is from A, B, C, D, E, F, G, H. K is at present all are full, that is nothing is there in them, we showing them as it is. Infinity is given as a default value or the default distance for all the nodes as we have not started. And PV stands for the previous node from which the distance has been calculated, and for the initialized array it is left as blank. So the initial array is, we don't know from where we starting with. Any node can be considered as a start node. So in this example, we have considered G as the start node. It is just an approach to solve the issue for this particular graph. So G is considered as the start node. As G is my starting element, it is added to the tree, whereas the distance it has travelled is 0 because that is my starting or the initialized point. And there is no previous node from where I can reach G, as that is my start position. So what do we do next? We find out from G where all we can travel. That is the out arrows going from G. The out arrow direction from G we have to calculate. From G, if you see here, I can reach D with a distance of 2 and I can reach H with a distance of 3. So in the distance array, we update the data to be 2 in case of the node D and 3 in case of the node H. And from where is it reached? It is reached from the source G. So in the PV, we write it down G. So it gives a very clear picture that I have traversed the node G. From G, I can reach the two nodes, that is node D with a distance of 2 and node H with a distance of 3. As we are trying to find the shortest path first, so among from G to D and G to H, I find the shortest value on the weights. Among 2 and 3, 2 is the shortest or the smallest element. So now from G to D, D becomes my start. So if you see here in the table, we have updated the value in the array K, that is select the minimum distance and write down T, which stands from it is added in my tree. As Dijkstra algorithm is an implementation of minimum spanning tree greedy approach. So it is added into the tree. Now from D, where all I can go. From D, if you see, there are two out arrows. One is going to F and another one is going to E. How do I calculate the distance between F and E? The distance between D to F is 18, but to reach to my node D, I have already taken a distance weight of 2. So 18 plus 2 will make it 20. So to reach the node F, the distance travelled is 20, and from where I have travelled from D. So in the previous node vertex, we write down D. And same thing applies when I travel from D to E. As the weight assigned to the edge D to E is 25, but I've already travelled the weight from G to D is 2, so 25 plus 2. So the weight assigned to the edge to reach the destination E is 27. And the previous vertex from where it is travelled is D. So in this table, if you will see, we have now 3 datas or 3 nodes which have been traversed, but from there I have not initiated the next node. So the spaces from which I have to select now, the nodes which I need to select for the start is among the node H with the weight of 3, the node F with the weight of 20 and node E with the weight of 27. So from this we find that H is the minimum weighted edge. So H with the value of 3 is chosen among 3, 27 and 20. So now from H where all we can traverse, we have to see the out arrows or the out degree of my H. So the out degree of H is from H I can traverse to B, and from H I can traverse to A. So in front of A, we write down the distance travelled to reach the node A. And the distance travelled to reach the node A is, if you see, H already has a weight of 3. And between H and A, the weight assigned to the edge is 4. So 3 plus 4 is 7. So to reach the node A, the distance travelled is 7. And the previous vertex from where it has travelled is H. Same thing for the edge B. When I am travelling from H, B, the node B has a weight of 9. And with the weight of 9, H has a weight of 3. So 9 plus 3 makes it 12. And the previous vertex from where it has been travelled is H. So you will see here from the table that we have traversed G, H and D. And the non-traversed nodes are A, B, E and F. Now again, out of these 4 nodes which are existing, we have to choose the minimum weighted node. And the minimum weighted node with the distance is A with 7. So now we will consider A. From A, where all we can traverse. From A, if you see, we can traverse to B. But A has a value of 7 and B, that is from A to B, has a value of 8. So 7 plus 8 will make it 15. But the minimum distance travelled, if I am reaching B from the previous node H, is 12. So we don't disturb that and we leave it as it is. And from A, I can even traverse to F. And if I traverse to F, the edge weight between A to F is 10. And the value of the distance travelled to reach A is 7. So 10 plus 7 makes it 17. So what we do? We replace the distance travelled in the node F to 17. And what is the previous node? We have replaced the previous node from D to A, as I take the distance weight of 17 to reach F from A is 17, whereas if I was reaching it from D, it was 20. So in the table, we have replaced that. Now we again have 3 values, that is B with the weight of 12, E with the weight of 27 and F with the weight of 17. So the minimum distance is 12, which is for the node B. So we now take B as the node. Now from B, where all we can traverse. As we are traversing, in the index we write down T so that we know this particular node has been traversed and it has been made in the tree. It has already formed a tree. From B, where all I can travel. From B, I can go to C, and from B, I can go to C. B has a value of 12, that is distance traveled to reach B is 12, and from B to C is 4. So 12 plus 4 makes it 16. And from B, I can even traverse to E. And the value of traversing to B is 12, and from B to E is 22. So we replace that and we write over there 22, as the previous one to reach was 27. So to reach the edge E, now when we are reaching to E was 27, I was approaching E with the previous vertex as D. Now 22 is less than 27, so we replace that, and the distance is replaced as 22 and the previous vertex is changed to B. You will see as we are recalculating, the shortest distance path is being calculated, and we keep on replacing the distance which is being calculated again and again so that I can find the shortest path first. Now again from 16, 22, 17, we find the minimum value which is 16. So now C becomes my start node or the root vertex from where I start. Now from C, where all I can go? From C, I can go to D. But D has an approach of 2, so that we will not replace. And from C, I cannot go anywhere else, so we leave it as it is. Now, the next node which comes is update any unselected node which is there. So, there is no updation at present needed, so we leave the tree as it is and then we move on to the next node. And in our next node, out of 22 and 17, we take the node as F. Now once we've considered F, now to traverse from F to E, what we do? When I'm reaching E with a value from B is 22. F has a value of 17. Now from F, when I reach E, it is 17 plus 2. That makes it 19. So what we do? We replace the node to reach E is from the previous node F with a value of 19. So the distance of E has been recalculated and any unupdated selection is updated again and again. Now the only node left is E. So what do? We select E and E has got a fixed location from the node F. So now we have visited all the possible nodes and found out the shortest path first to reach each and every node. This is the final solution for the Dijkstra algorithm, implementing the shortest path first with multiple destinations. As we can see that to reach a particular node, there are multiple paths available. And then what we see, what is the order of complexity for the Dijkstra algorithm? We find the minimum, so it takes the big O V time, that is, it keeps on evaluating with the time. The outer loop iterates with V minus 1 times. What do you mean by the outer loop? Outer loop means that when I am continuously iterating for the values from source to destination, and the complexity of my Dijkstra algorithm is big O V square, that is, with a vertex, as my number of vertex increases, it multiplies in a double manner. And for the optimal dense graph, the number of edges is equal to big O V square modulus, that is, it is working for all the positive values of the nodes. There are no negative values which are taken. That is, I am not implementing the Dijkstra algorithm at present for the negated graph. That is, the distance traveled can be shown or written in a negated value. With the modulus, it shows that all values, all the distances which are written over here are positive. And the suboptimal for the sparse graphs is E for all the edges is big O for all the vertices. And again, if the graph is sparse, we maintain the distance in the priority queue. That is, all the nodes are sorted and the distances are put in a priority queue. We keep on inserting the shorter distance which is produced when we are changing with the previous vertex, and we are recalculating the distance as it continuously goes in a recursive manner. And this being a greedy algorithm, it keeps on changing wherever it finds an optimal solution, as greedy algorithm works or is always implemented to give us an optimal solution. So, the best time complexity for the Dijkstra algorithm is big O for all the edges with a logarithmic value of p is how the graph will increase with a time complexity. Thank you.